Good afternoon, everybody. We are going to commence the oral session on topic 2.2, challenges of on-site inspections. This oral session is a continuation of the poster session that we have this morning with a few posters on this topic. One of the challenges of this oral session is to end at time, because we understand that we are the barrier between you and going to drink something in the city or something else in this very warm day. So this is something also for the speakers here. I have the honor to present the first speaker, my good friend Emily Schultz-Fellenz from Los Alamos National Laboratory, and she will introduce some work that she has done on new horizons for characterizing treaty-relevant events and the benefits and challenges of using robotic systems. Emily, please.
This is not a laser pointer.
Okay. Thanks, Gustavo. I appreciate it. It's wonderful to see familiar faces in the audience. Thank you for sticking around late on a Thursday afternoon. Yes, I'm going to be speaking to you today about new horizons in the use of robotic systems in on-site inspection for treaty-relevant events. I'm going to talk about the benefits of using such platforms. I'm going to give a case example that our team employed in the use of such systems for characterization of an underground explosion in the United States. And then I'm going to talk specifically related to our team's work on some of the challenges that we have faced and how those challenges may translate to on-site inspection applications for the CTBT. So let's start out by making sure that we are using consistent terminology through this presentation, because this is an evolving science and an evolving mission space. Making sure that we're using similar phraseology or terms throughout is important. So the definition that I'm using in this presentation for robotic systems is the engineering and operation of machines that can autonomously or semi-autonomously perform physical tasks on behalf of a human. I'm going to focus most of this presentation on semi-autonomous applications. When we get to the challenges, I will talk a little bit more about autonomous operations and some horizon space and difficulties that we face there. But you'll see in this slide that the term robotic systems can encompass vehicles that can carry sensors that are both terrestrial and airborne. And as probably everybody in this audience understands and appreciates greatly, there's different ways that terrestrial and airborne OSI techniques are viewed and can be applied in a treaty framework. And that's not something that's lost on this presenter or our team. And it's certainly something that is going to be brought to bear in discussions on the use and adoption of such technology if and when these discussions reach the floor of places like Working Group B. The use and the application of robotic systems as platforms against which scientific data can be acquired has expanded tremendously in the last 5 years. There are a host of publications, in fact, entire journals that are dedicated to the use of robotic systems for data acquisition for science and technological applications. You'll see that our field team has a prominent feature in this slide deck. The upper center photo is a picture of our team operationalizing one of our uncrewed aerial systems, UAS, or airborne drones, on-site at Los Alamos National Laboratory, equipping it with a sensor ready to go up and fly for a mission. These techniques have been applied in a number of other situations around the world, including for disaster monitoring, like the beautiful shot you see in the upper right of the drone silhouetted by a volcanic eruption in Hawaii. There are autonomous creatures like the Boston Robotics Spot Dog in the lower left. Hopefully many of you have seen that in action downstairs near the helicopter flight simulator. There are tracked robots that you can take into underground complexes, which have very direct OSI applications. And you can see that there's a number of different sensor configurations and in fact sensor suites that can be deployed on these for multimodal data collection and data fusion applications. These platforms facilitate the collection of many different kinds of visual observation, geophysical, multispectral, and radionuclide data sets that tend to do better at not putting humans at risk. And these are wonderful benefits in the use of these systems for CTBT on-site inspection, where you may be faced with a host of environmental and other site conditions that might be risky to personnel. The sensors that we show here in this slide include visual red, green, blue electro-optical cameras, gamma detectors, magnetometers. We show a laser scanner, which I did want to link to a presentation by my Sri Lankan colleague yesterday, identifying accurately some of the difficulties and challenges in on-site inspection in tropical environments. Sensors that can be deployed from mid-altitude range on airborne platforms could help with the tree canopy penetration issues that were so correctly identified there and help facilitate efficient on-site inspection in environments like that. So I'd like to move to the case example that our team executed. We did detailed, high-resolution, image-based change detection over the site of an underground, controlled, conventional high-explosive experiment in Nevada over several different iterations of an experimental series. So there were multiple different underground explosions that took place. Our team took the effort to install a very dense network of geodetically surveyed ground control points, then captured imagery from uncrewed aerial systems both prior to and immediately following those explosive experiments underground. The goals of our work were to obtain the highest possible resolution digital elevation models of the site and do difference calculations to determine what, if any, detectable surface signatures were present or resulted from those underground conventional explosive experiments. I give that caveat here because I will talk about that as we talk about data processing and challenges, because our objectives were not necessarily the same as those that would be expected in CTBT OSI. So what we did is we flew our drone in a very controlled flight pattern, which you can see in the upper right-hand corner. The lower right-hand corner shows you image density overlap acquired in that spatial regime. The purple colors show regions where we have 10 plus images in a single location, which helps give you greater fidelity in data resolution of your digital elevation model that's obtained from imagery. What I would like to highlight here is the fidelity of both the imagery and the digital elevation models that these methods are able to obtain. So without putting people in a space where they are exposed to emplaced conventional high explosives, without putting people in a risk space that might involve other ground disturbance following one of these underground explosions, we were still able to obtain imagery that presented sub-centimeter scale signatures to us. You'll see that we have pointed out specifically places where footprints can be identified, geomorphic rills where water flow has disturbed the ground surface. And you can also see changes in engineered features from before and after an explosion, where things like cables, diagnostic cables and sandbags have moved as a result of the underground explosion. These signatures are otherwise very challenging to detect unless you are pressing for extremely high resolution data acquisition, and can do so in a way that does not disturb the environment that you're trying to characterize. So outside of the natural and anthropogenic environment, we're also able to use structure from motion photogrammetric techniques, something that was described in a separate presentation by my colleague Brandon Crawford earlier this week, applied to standard electro-optical imagery to identify both vertical offset and horizontal ground shift that resulted from these conventional high explosive underground experiments. On the left-hand side, you see the vertical uplift that resulted from a series of underground explosive experiments. The warmer colors represent uplift, cooler colors represent subsidence. And in the rightmost panel of images, you see arrows indicating direction of lateral or horizontal ground shift that were also experienced at the same location. So our methods using high density imagery from drones were able to identify surface changes at very high resolution from these underground explosive experiments. I'll point you to a couple of papers from our team if you're interested in learning more about our methods and our results. This is not without its drawbacks. Because we were driving towards the highest possible data resolution that could be obtained, we acquired thousands, if not almost tens of thousands, of single frame images. The processing time involved in using all of those images to create digital elevation models was tremendous, not just in computational time, but in human time required for data analysis. Now, I mentioned before I wanted to put an asterisk by the linkage between this work and CTBTO OSI applications. It may be very difficult to identify a need space in CTBT on-site inspection where such resolution is required. But the use of these techniques prompts the need for a conversation amongst technical experts and ultimately amongst policymakers as well about what data resolution is sufficient and how does that need to be fused with other data modalities obtained by OSI to drive towards the sorts of documentation and information requirements that would be required to be produced from an on-site inspection. So to identify the types of signatures that you see in the images above, which is the signatures of a borehole that vented both water and mud as a result of an underground explosion that took many, many dozens of dedicated computational hours and many more dozens of hours of human computational time to identify the boundaries of that, its magnitude, and link that to specific activities from other data modalities. I want to conclude by identifying some other challenge topics that definitely need to be discussed when using these types of techniques in on-site inspection. And the first one I'll point to is in the upper left, where you see a bunch of very happy smiling faces on a day where I think it happened to be almost 45 degrees Celsius. We were out in the field executing a mission related to the characterization of these underground explosions. It takes a team, in our world, it takes a team of at least 6 people to execute these sorts of flight operations. It's not inconsequential when it comes to human capital required to do that. And when you talk about this in the context of OSI, where you have a limitation on personnel, this is a very serious constraint that needs to be discussed about how to do this effectively and safely with the right amount of people. You're talking about equipment that has high-speed rotors in some instances. batteries, you have fire hazards, you have rotational hazards. Things can go off normal. The operational safety envelope is something that needs to be carefully understood. I've already spoken about sensors and data processing, and here's where I'll link very quickly to automation or autonomy in the operation of robotic systems. We can talk about autonomy when it comes to the actual vehicle operation. We can talk about autonomy when it comes to data processing. We can talk about autonomy when it comes, or automation when it comes to data analysis, but all of those things are different. They have different requirements, and they have different levels of evolution at present. And I will say, developing autonomy often takes you to a place where you require training data. And the training data that I know that publicly exists for signature detection of underground explosions using robotic systems consists of the author you see here and our team, and our publication's number 3. So we don't have a whole lot of information on that topic yet. There is also the pressing question when you are talking about airborne vehicles of where this space sits with regard to initial and additional overflight constraints. And it is an open topic of discussion. It is controlled by a human who is on the ground. In principle, the inspected state party would have full access to vehicle telemetry and data acquisition from the ground, but they can't physically board the aircraft because nobody physically can board the aircraft. So there are a number of additional initial and additional overflight considerations that link to this problem. And I did want to, again, highlight the photo of our wonderful PTS staff in the helicopter that you can experience downstairs. I want to thank you for your attention. I'm happy to take any questions if we have time or speak with anyone afterwards. Thank you.
Thank you. Thank you very much, Emily, for this very interesting presentation. Any question from the audience? Yes, please.
Emily, thanks a lot for this. You mentioned about the need for an honest conversation, right? I'm sure that you had at least an internal conversation with yourself. How would you apply this for OSI, with which resolution, for which purposes? Do you mind sharing that with us?
That's a wonderful question.
Thank you.
And I thank you for bringing it up, Luis. It is one that, to answer fairly, I will have to come at it from my own expertise. The application of this technique, both for position finding and for anomaly and artifact detection that can be linked with other signatures, and I speak about that from the VOB MSIR regime, I really think that's where the power lies. But in my opinion, this would probably not be a technique that would be applied until the inspection team focuses in on some select areas, because I am less familiar with the application of this kind of toolkit in a broad area search, in something that would be on the 1,000 square kilometer order of an inspection area. So that's a really great conversation. I think people who maybe have more radionuclide expertise might have a different answer than I'm giving you right now.
Any other question? Yes, Franz.
In terms of weight, what kind of payloads are these?
Excellent question. So Franz's question is, what kind of payload capacity do these robotic systems have? They're highly variable. I can tell you from the system that we use, if we had no constraints on our pilots, The maximum capacity that our heavy lift drone can carry is, I'm looking at Brandon here, I want to say it's somewhere on the order of 50 kilos, perhaps a little bit higher than that. But our pilots are not qualified to operate at that level. You also trade payload capacity for battery lifetime. So with higher payload comes reduced battery lifetime and more need to land and replenish batteries and relaunch.
Yes, Aled, last question, please.
Just a comment about the resolution. I think it's important to match the resolution to the observables. So basically, we need to cross-match the observables that we're looking for against, and that will give us then the resolution that we need.
Thank you for that point, Aled. That's a very good one. And that may be something that links, as this conversation evolves, understanding what different robotic platforms at different standoff distances can realistically obtain in terms of data resolution could help us understand what sorts of signatures could be detected in those regimes.
Okay, thank you very much, Emily, and a round of applause for her. And
Okay, good afternoon. We have one more presentation in this session, and the presentation is on the use of satellite imagery and other open source information for nuclear test site monitoring, and will be delivered by Marcy Fowler.
Great, thank you all. So I realize that I have now become the barrier between you and the... thank you. My name is Marcy Fowler, and I'm happy to be here from Open Nuclear Network. We are located here in Vienna. And I'm going to be talking to you about the commercially available side of imagery. So we'll talk about how satellite imagery that is commercially available can be used for nuclear test site monitoring, the relevance, of course, to CTBT verification. And I'm also going to talk to you a bit about a case study that we've been working on at ONN, looking at the North Korean nuclear test site activities. So first, I'll give a little bit of background on the use of satellite imagery that is commercially available in nuclear test site monitoring. Now, monitoring of nuclear test sites goes back decades. Governments were monitoring nuclear test sites in even the 1960s when the US was monitoring nuclear tests in the Soviet Union and in China. But commercially available nuclear test site monitoring has actually been being done since the 80s even. In 1986, the Space Media Network actually identified indications of a coming nuclear test at the Semipalatinsk site in the Soviet Union. In 1992, the NGO in the UK called Robotic identified precisely when and where a nuclear test would take place in China. Fast forward to today, and there are several NGOs, institutes, and think tanks working in the space using commercially available satellite imagery to monitor and analyze nuclear tests around the globe. So this is another area where the technological advancements have been moving at a very rapid pace. Not in the last 5 years, but in the last couple of decades, commercially available satellite imagery has been advancing very quickly, especially in the number of the satellites that are being launched, as the cost of the launching actually is reducing very quickly. The size of the satellites is going down to the point where we're having these small sats that are actually available now. At this point, the number of commercially available satellites in orbit are actually about 70% of all satellites are commercially available, and that number, that number is actually increasing quite rapidly as well. So the bottom line is the spatial resolution that is available from commercial imagery and the temporal resolution are constantly increasing. So you're getting better images more frequently, and the price is going down. Competition continues. This is very good for international organizations, non-governmental organizations, and think tanks around the world because it gives us a more transparent and open way of monitoring these test sites. And other things, of course. So some of the key applications for monitoring the test site would be both in the pre-test and in the post-test time. So before a nuclear test, what you would look at the test site is you look at identifying a potential nuclear test. So you'll be looking at changes in the infrastructure of the location, for example, looking at surface deformation and excavation activities indicating new tunneling, for example. You're also looking at looking for towers, cables, things that would indicate more developments and the level of preparation for a nuclear test. Then, of course, after a nuclear test would take place, there's more that can be analyzed. So you would be looking for cratering, you would be looking for avalanches, and the goal there is to learn more about the test itself or potential test. And with that, you can actually take information from satellite imagery and even calculate potential yield of this potential test. So as I mentioned, there are different satellites that are going up quite regularly, and this is also increasing in the type of satellite imagery that is available. So there is, of course, optical imagery that's available in higher and higher resolution. There is also multispectral imagery that is available in commercially available sources now. Thermal infrared imagery is also available, and synthetic aperture radar data as well. And for nuclear test site monitoring, high-resolution optical imagery and the synthetic aperture radar, or SAR, is the most important of the sensors. Allows for, of course, precise geolocation, but also, as I said, would allow for a yield estimate when you would bring together the information from the imagery together with explosion modeling. So while these capabilities are growing and improving quite regularly, it is not necessarily new in that it has been foreseen. So currently, the CTBTO does not have the capability to monitor in a pre-test time frame for a coming nuclear test, but it was foreseen that each state party should undertake to cooperate with the organization to examine verification of potential additional monitoring techniques, and it is specifically pointed to satellite monitoring. So this was foreseen in the CTBT itself, that this would be a technique that could be added to the toolkit of the CTBTO in the future. Now, of course, the CTBTO would already have the capability of using satellite imagery in an on-site inspection regime, but this is, of course, for expanding the pre-test analysis as well. So some of the potential, hang on a second, small tech problems. There we go. Some of the potential applications run through all of the time of a test, from monitoring for a potential test for the CTBTO, investigating potential test locations, indications, bringing this together with other information that they receive from the IMS, from state parties. Also in the pre-inspection phase, so preparing for an on-site inspection, of course, this is a part of the on-site inspection preparation, delineating the possible area, and this would, of course, help things like the drone, trying to decide exactly where you would want to deploy other techniques, site familiarization generally for the team that would be going into the field. In the inspection phase, clearly already included in the techniques, and then also in the post-inspection phase for a continued monitoring regime after an inspection would be concluded. So I've talked a bit about how this could be used in CTBT, and now I'll talk about the case study that we have been looking at in North Korea for the last few years. So this case study illustrates how commercial imagery can be used to help in a deeper understanding of a nuclear testing program. So knowledge of the overall program is actually key, and I do want to say satellite imagery is what I'm talking about, and it is a very important component, but it should also be integrated with other types of information. So what I'm showing here is an image that was actually released by North Korean state media showing information about their Pyongyang nuclear test tunnels. This type of open source multimedia information can be integrated with satellite imagery to learn a lot more about the actual test site itself. So information integration together with satellite imagery is really quite a key. So a bit to what we have found. So we've been monitoring this area for the last couple of years, and then early in 2022, we actually saw quite a bit of activity in around the third tunnel of the Pyongyang nuclear test site. In 2018, the North Korean leadership actually brought in international media and destroyed the primary tunnel's primary entrance. And so this tunnel was thought to have been destroyed, but there is actually a secondary entrance to Tunnel 3. And starting early last year, we were seeing signs of movement, a lot of heavy traffic indications and indications of excavation. So spoil piles indication around the secondary tunnel entrance. So after last summer's activities into the fall, there seemed to be a lull in activity. There were no longer additional excavations, but we did continue to see traffic continuing, and there seemed to be a continuation of personnel being located there. And the status of that remains the same today, in that there has not been any additional excavation work. So what our conclusion is that with the information we've seen from satellite imagery combined with other information from open sources, we've concluded that the third tunnel of the Pyongyang nuclear test site is likely available for the use of a nuclear test, should such a decision to take a test would actually be made. So then, to conclude, there are many new opportunities that are being presented for verification, both in IOs as well as in civil society, think tanks, and NGOs around the world, thanks to the increasing availability of the commercially available satellite imagery. There are many applications for the CTBTO, even in the use of this open source information. Although the CTBTO is not using it for a monitoring regime at this point, other IOs have been using satellite imagery for monitoring regime, for example, the IAEA. And then finally, we can all share lessons together in our use of this information. We can share lessons learned between states, IOs, and civil society, like what we're doing here today. So that's it, and I look forward to your questions. Thank you.